Hello guys, so in this recording we're gonna solve some examples, basically some of the homeworks that we took so far. We're gonna start by this example, which is basically homework 18, which is basically a common emitter amplifier. So how could we know it's a common emitter amplifier? Basically, look at the input and the output. So the input here is at the base and the output is at the collector or connected to the collector. So the signal, B signal, the main source of the input here is connected to the base through the capacitor and this signal here, which represent our signal basically. And the output is basically this load, and it's connected to the collector through the capacitor. Okay. One thing here that we didn't practice in lectures is that we have a current source, DC current source, as one of the ways to bias the circuit. So we started biasing using multiple ways. This is one way, is to connect a current source, but basically this current source is not a current source in a sense you have equipment, some equipment in the lab, like a voltage source that can be converted to a current source. It's not this big device. This current source is basically another circuit which has also a transistor that can be modeled as a current source, but this is not our, this is beyond the scope of this course. Okay, this is called the current mirror circuit. So it's a circuit using a transistor. It's biased in a way that can be just replaced by a current source with a fixed current like this. And in that case, this current source is providing 2 milliamperes. Okay, good. So let's start by analyzing this circuit, in DC, and then go to EC and calculate, basically everything, our input, our output, AV, AV node, and GV. Okay, so let's start by the DC analysis. So in DC, we're gonna consider any capacitor as an open circuit and cancel any AC sources. Okay, so basically we have just one AC source, which is V signal here. So this guy will be shorted, and we have 3 capacitors. So basically these capacitors will be open. So the circuit can be reduced in DC like the following. Okay, good. So let's now try to calculate. So we do the DC for 2 reasons, basically: to calculate R pi or GM, whatever you like. Both are equivalent and both are, function of one another. And to be sure that we are really working, in the active region, because this is amplification, application. So we must be working in the active region. Okay, we are, this for sure, this is an amplification circuit. The purpose of this circuit is to, verify and make the AC analysis. So don't worry about, the verification. So we should get, R pi, okay? And R pi is equal to VT over IB. So we must know IB. Where is IB? Here is IB. The current that goes into the base. Okay. Where is IE? IE is the current that's coming out of the emitter. And look here, IE is just the current source current. So basically IE here from the circuit is basically 2.2 milliamperes. It's a constant. And beta for that transistor, it's given in the question, it's 100. But we know that IE equal to IE over beta plus 1. You can, approximate that if beta is, very big, like 100, as IE over beta. So 0.2 over 100, it's 0.002 milliamperes, it's 2 microamperes. That's basically IB. Okay. If you want to extend, the DC analysis and create many other stuff like VB, VC, because the question in the homework we're asking about these parameters. Let's do it. Where is VB? Here is VB, the voltage at the base. Okay. Good. So IB is flowing in that branch. It's flowing in that way like this and going into the base. Okay. So, and VB is the voltage across this resistor. It's a voltage from the ground to this point, the base. Okay. So VB, or let's say IB, is equal to the voltage at that point, which is 0, minus the voltage at that point, which is VB, over the resistor. So 0 minus VB over the 100 kilo ohms. Why we didn't say it's VB minus 0? Because it's flowing, when we calculate a voltage, we subtract the source, the node at which the current goes from to the point at which the current goes to, and divide by the resistor. So the current here is going from that point to that point. So 0 minus, VB over the 100 kilo. This is equal to 2 microns, or you can say milliampere, because you're gonna, multiply now the milli by and the kilo, so they will cancel each other. So basically VB is equal to 0.002 milli multiplied by 100. So that will be 0.2 volt. That's, or minus, I'm sorry, minus. Because minus VB is equal to IB multiplied by 100 kilo ohms. So multiply both sides by -1, so it will be minus. And here there is a purpose from this equation to see that yes, VB can be minus. What really matters here is if IB is positive or negative. Okay, since we are in active region, IB must be positive, and IB is positive here. VB doesn't matter; it can be negative, whatever. But at the end, IB is positive and IE is positive, and of course IC will be positive because IC is equal to approximately equal to IE, so it's also 0.2 milliampere. What else was required? VC. So VC is the voltage at that point. We said that IC approximately equal to IE, so it's 0.2 milliamperes. IC is flowing in that branch, flowing from the 5 volt to VC, going into the collector. So IC is equal to the point from which it goes out, which is the 5, minus the point that is going to, which is VC, over the 20 kilo ohms. So this is equal, or we can say from that 5 minus VC equal to 0.2 milli multiplied by the 20 kilo. Milli will go away with the kilo. So, and the 0 will cancel the point, or the point, I mean. So it will be 4. And from that, you know, when you multiply by -1 and, you know, add 5, it will, VC will be 1. 5 minus 1 is 4. You know? Okay, that's basically VC. What else was required? GM, you know, GM is VC over IT. So this is also GM is VC over VT. VC is known one. VT is 26 millivolt. I'm sorry, not milliampere. Millivolt. And you should check because VC is volt and VT is also volt. So, you know, GM is dimensionless. That's correct. Okay. And you can, you know, get that easily. Or you can consider it 25 millivolt. It's okay. Finally, our pi was required. Our pi is VT over IB. We can consider VT is 25 just to get the same exact numbers as, you know, the assignment. And the IB is known. It was buoyant where it is. Yeah, keep it in that way so that the milli will go away with milli. Okay, and I'm sorry, this is millivolt, not milliampere. Volt over ampere gives ohms, of course. Okay, so that will be, that's big, you know, because you're gonna multiply the 25 by 1,000. So 25,000 over 2, it's 12, you know, yeah, 12,500. So 12.5 kilo ohms. Yeah. Okay, that's the DC portion of this, you know, example. Let's now do the AC. In the AC analysis, we short the capacitors and we cancel now the DC source. We have here 2 DC sources. We have the 5 volt and we have the current, you know, current source, this guy here. What a current source do? To cancel a DC, any source basically, to cancel a source, either a voltage source or a current source, we cancel its effect. So for the 5 volt, a battery, I mean a voltage source, what it do? A voltage source increase the potential of 1 point. It's a positive terminal, then the negative terminal by the amount of the battery. So that means if this is V1, if this is V2, so V1 will be equal to V2 plus 5. Okay. To cancel its effect, make V1 is equal to V2. How we do that? Just short it. Then you cancel its effect because now V1 is forced to be equal to V2. How to cancel a current source? To cancel a current source, we cancel its effect. Its effect is that the current source provide a constant current in its branch. So if we have a current like this, 1 ampere providing, you know, so this branch all the time has 1 ampere flowing into it. To cancel its effect, just open the branch. We can open like this, so the current will be 0. Okay, so that's basically what we're gonna do. So we're gonna short the capacitors like this, open that guy, and short that guy. When you short it, because it's this 5 volt, to do it in, you know, this 5 volt is basically a battery like this with its positive terminal connected toward, you know, the resistor 20 kilo ohm, and the negative is toward the ground. So when you cancel the source, you just connect it like this. So this will cancel that guy. And that will be open. So you just remove this branch, this little branch here, just remove it completely. So let's draw the circuit after we do these modifications. So number 2, the AC analysis. So I'm gonna have a ground, then the capacitor, the resistor, let's call it RC. Then this capacitor will be short. Let's call this resistor RE. Okay. And this will be short as well. So let's call this RL. Then we have here 2 branches connected to the base. One branch with this resistor. Let's call it RB. And then the other branch which has V signal and R signal. Okay. Now, one little touch we need here is to replace the transistor and put its equivalent circuit. This is common emitter. We usually use this model for it. Beta IB, and here is IB. This is the base, this is the collector, this is the emitter. Then connect the rest of the circuit. Here is the emitter. Between the emitter and the ground, there is a ray. Here is the collector. Between the collector and the ground, there are 2 branches. One is RC, and the other is RL. And of course, this is V out between this point and the ground. The voltage across RL or RC, both are equivalent because they are in parallel. Here is the base, and between the base and the ground there are also 2 branches. One is RB, and this is RB, by the way, which we already know. It's 12.5 kilo ohms. And then R signal and V signal. That's basically the circuit that we're gonna, use to get all the parameters we need for the amplifier. So let's start by here. Let's check what was required here. Our input in the beginning. Our input is between these 2 points, as indicated in the question. You can say that our input is this resistor here, RB, parallel with another R input, which we'll call R input dash, just to differentiate it or discriminate it from, make it distinctive from our input. So I'm gonna draw the rest of the circuit here, and let's divide it in 2 halves. So we're gonna have this resistor, RL, RC, beta IB, RE, RBI, and we're gonna put here VX and IX as usual, and Rn dash is Vx over Ix. And here is IB. Ix is easy, equal to IB. Always make your parameters like Ix, Vx function of only the resistors. IB small is unknown. Okay. So when I say IX is equal to IB, I mean that I'm gonna determine VX in terms of IB as well. So when we divide them by each other, IB must be cancelled out. So let's do that. VX is the voltage here in that loop from that point to that point. The current flowing in R by is IB. The current flowing here is IE small, which is or the addition of IB and the beta IB, which is IE, you know. So that's basically beta plus 1 IB. So from that loop, VX equal to IB R by, just make Kirchhoff here, plus beta plus 1 IB RE. This is just Kirchhoff from that loop 1 here, loop I, whatever. Okay? So now Rn dash equal to, just to divide Vx by IB. So IB will just cancel out, so it will be R by plus beta plus 1 RE. So at the end, our input equal to R capital B capital parallel with Rn dash, which is R by plus beta plus 1 RE. That's a big one. That's good. I mean, you always want the input resistance to be high. This one is high. And why it's high? Because of the introduction of RE the degenerate resistance. If you guys review our previous topics, when we put emitter resistance, it usually increases our input. Okay, AV note. So this is number 1 here. Number 2, AV note. You can do this in different ways. Since EV is also required in number 10, or it's required, whatever. So you can do EV first, then take the limit and find EV. But whatever you like, you can do EV note in multiple ways. Okay. So let's do that. So EV note is a gain. It's a pure gain. It's a pure gain of the circuit, the intrinsic gain of the circuit, without our load or our signal, without the effect of our signal, without the effect of our load. So it's basically to determine EV note, we should consider our load equal to infinity and our signal equal to 0. You can see so. So the gain when considering our load equal to infinity, our signal equal to 0. Or you can say it's the voltage at that point, VO, without RL, okay, over the voltage of that point, which we can call Vn. We can draw the circuit using just without RL and without the input signal. So it will be like this, something like this. Or C here. RE, beta IP, R pi, RB capital, and here is V input. Of course, V input will be V signal if there is no if our signal is equal to 0. Okay, and here is VO. What is VO? VO is the voltage across RC. The voltage across any resistor is the current multiplied by the resistor. What is the current flowing in RC? It's beta IP. But it's negative because it's flowing. So it's flowing from bottom to up, while VO is the voltage of the top point in reference to the ground. So VO equal to minus beta IB RC. What is Vn? Vn can be calculated from that loop again here. There's a voltage across R bar, RB, I'm sorry, R capital B capital. From that point to that point. So here is again IB, and here is again beta plus 1 IB, just like this one here in the number 1. So Vn equal to IB R by plus beta plus 1 or IB RE. Now AV naught equal to VO over Vn. So basically it will be minus. IB will go away because it's a common factor in either VO and Vn. So it will be beta RC over R by plus beta plus 1 RE. That's AV naught. Now we're gonna calculate, AV. AV is gain without, when we consider the load, but we don't consider our signal. So we can consider our signal is equal to 0. Okay. So we can expect, because of our experience, if you, do a lot of, analysis like this, AV will be beta, same equation, but beta RC parallel with RL, because this is the only difference. So the only difference when we try to calculate AV is that we're gonna add RL, but we're gonna still, consider our signal is equal to 0. So Vn is equal to V signal. Okay. So in that case, let me draw it in another color. So we have the same. So number 3, AV. AV is a gain when considering our signal equal to 0. So RL is there. So we're gonna have the same circuit. So I'm gonna just copy and paste. And we're gonna add to it our load. I'm gonna add it in another color so we know this is the only addition. Now, what is the difference? The input will be also calculated from the same loop, so the input will be the same. Same V input, this guy. But VO is different now. VO is the voltage across RL or RC or the parallel combination, because we don't know the current in RL, we don't know the current in RC, but we know the total current that flows in, in the parallel combination of both, which is beta IB here. So it's minus beta IB RC parallel RL. So AV, when we divide, it will be minus beta RC parallel RL over R by plus beta plus 1 RE. That's basically AV. Okay, what else was required? GV. GV is simple. Let's do it in green or whatever. So we know that GV is the overall gain, the gain when considering everything, So now our signal is not 0, RL is not 0. The same, same circuit basically. And we know that if we consider everything, then it will be a function of AV. And it will be AV Rn over Rn plus R signal. Okay. If we calculate the values, let me put the values here. Say this will be 20 kilo ohms. AV naught will be just to have a sense minus 80. AV will be, of course, less minus 40, because RC is equal to RL, both are 20 kilo ohms. And GV will be even less. It was minus 20. Because our input is equal to our signal. Okay, so that's basically, you know, the requirement for this homework. So we're gonna go now to another example, which is basically homework 19. See you. Bye.